Climate change is reshaping ecosystems worldwide, on land and at sea. The lives of marine turtles, travelers of our oceans, are especially threatened. Rising temperatures are shifting where species live, altering breeding timings, and reducing biodiversity. For marine turtles, these changes cut deep. Their physiology, behaviors, and reproduction are tightly linked to ambient temperatures. Here's one of the most critical issues: they don't determine sex genetically. Instead, it's all about external temperatures. During the middle third of incubation, known as the thermosensitive period, nest temperature decides whether a hatchling becomes male or female. The critical temperature, the balance point, is around 29 degrees Celsius for green turtles, though some populations vary slightly. Above these temperatures, females prevail; below, males dominate. Just a single degree shift can tilt dozens of hatchlings one way. With global mean surface temperatures projected to climb by 0.3 to 4.8 degrees Celsius by 2100, many turtle nesting beaches are already producing mostly females, and warming could push them toward all-female outcomes. If nest temps exceed approximately 33 to 35 degrees Celsius, embryos can fail to hatch altogether. And even below that, warmer nests produce weaker, smaller hatchlings. Ascension Island, a UK territory in the South Atlantic. It hosts one of the world's major green turtle nesting aggregations. Beaches are hot, barren, nearly treeless, and nesting already produces approximately 75% female hatchlings. But darker volcanic sands absorb more heat, pushing nests near their upper thermal limits. This backdrop made Ascension the perfect natural laboratory to test shading strategies. Researchers investigated whether artificial nest shading, using shade cloth, could cool nests enough to improve hatching rates and rebalance sex ratios. They compared shaded and unshaded clutches relocated to a hatchery, and untouched nests left in situ, across two contrasting beaches. Here's what they found. Artificial shading lowered overall nest temperatures by 0.5 degrees Celsius on the cool beach, and up to 0.9 degrees Celsius on the hotter one, and during the thermosensitive period, cooling reached 1.2 degrees Celsius on the hot beach. But how did that translate to outcomes? On the hot beach, shading increased hatching success by 19 to 23%, lifting it from potentially hazardous to safer territory, up to approximately 84%, comparable to cooler sites. On the cool beach, hatching success hovered around 90% across the board, already high, so shading didn't change things, but it did shift sex ratios. On cooler beaches, shading nudged the proportion of male hatchlings significantly upward, by around 12%, where nests naturally hovered nearer the pivotal temperature. Artificial shading works, especially on hotter sands, by reducing temperature, boosting hatch success, and improving sex ratios. But the benefits vary with site conditions. They also discovered nest relocation impacts. Even unshaded nests in the hatchery were warmer than in situ controls, likely because hatcheries were farther from the cooling influence of the ocean. Other groups of researchers have tested shading and similar low-cost interventions in different locations. They have tested interventions like palm leaf shade, white sand covers, or irrigation, and they had encouraging, consistent success. Several studies were conducted in various locations, including St. Eustatius, where simple shading resulted in a cooling effect of 0.6 degrees Celsius. In Malaysia, the use of shade cloth resulted in a temperature drop of 1.3 degrees Celsius. While in Costa Rica, mesh shades achieved a cooling effect of up to 0.8 degrees Celsius. Cooling tools are not one-time solutions. They generally work, but their effectiveness relies on several factors, including sand color, beach microclimate, moisture, and rainfall. On Ascension, shading was experimentally applied to only 0.3% of nests. Scaling up would require extensive shade installations, costly, visually intrusive, and potentially harmful to beach ecosystems, including seabirds and vegetation. For large, densely populated sites, implementing shading solutions may prove to be impractical due to spatial constraints and logistical challenges. However, for smaller, critically threatened rookeries, such as those home to endangered species or located in vulnerable coastal areas, strategically designed shading interventions could serve as an essential interim measure. These targeted shading efforts could significantly reduce heat stress on nesting birds and protect vulnerable eggs, ultimately improving hatch rates and supporting the overall health of these crucial populations. Here are some alternative solutions to consider. Planting vegetation for natural shade. While this method can provide shade, it's important to be cautious about the potential introduction of invasive plant species that could disrupt local ecosystems. Improved coastal development planning. By carefully planning coastal development, we can mitigate the risks associated with rising sea levels and prevent the encroachment of the ocean on beachfront areas. Protection and restoration of nesting habitats. It's crucial to safeguard and rehabilitate nesting areas by reducing pollution, minimizing artificial lighting, and limiting human disturbance, all of which can negatively affect turtle populations. Harnessing phenological plasticity. This approach involves allowing turtles to adjust their nesting timings in response to environmental changes. Early shifts in nesting behavior have already been documented, indicating that such adaptability can be beneficial for their survival. But whether turtles can adapt fast enough across populations remains uncertain. Artificial shading can serve as an effective strategy to investigate the impacts of climate change, particularly in vulnerable ecosystems, but it should not be viewed as a standalone solution. To achieve a more sustainable outcome, it is essential to customize these shading solutions to the specific environmental and climatic conditions of each area. Moreover, these measures must be integrated into broader conservation initiatives, including habitat protection to preserve biodiversity, effective beach management to maintain coastal integrity, regulated light control to minimize disruption to nocturnal wildlife and ecosystems, and proactive sea level rise planning to safeguard communities and natural resources against imminent coastal threats. In summary, shading turtle nests can effectively mitigate overheating, protect embryos during critical developmental stages, and help achieve a more balanced sex ratio among hatchlings. However, this method is not universally applicable. Its efficacy varies based on environmental conditions and specific site characteristics. For example, shading techniques tend to work better on hot, dark beaches where elevated temperatures pose a significant threat to embryos, as well as on smaller nesting sites where the logistics of implementing shading strategies are more manageable. Conversely, in larger rookeries, such as Ascension Island, where natural environmental conditions still provide a viable incubation environment, the traditional approach of allowing nests to incubate naturally remains a sensible option for the time being. As climate conditions continue to evolve, ongoing research and monitoring will be crucial to evaluating the long-term effectiveness of these intervention strategies. Still, shading tools offer real potential in the climate adaptation toolkit if used smartly, locally, and sustainably.